Okay, so the derivative is the limit as h goes to 0 of f at x plus h minus f at x divided by h. So that's from last semester. All right, so let's look at a general exponential function. Let's say we have a to the x, and we want to find the derivative of that, f prime. How do we do that? Okay, so we're going to put that into the formula here. And now we have to do some algebraic manipulations. Now remember, when you have a to the x plus h, that actually is a to the x times a to the h, right? When you have the same base, you're multiplying two different expressions, and it turns out that the going back the other way, going back from here to here, you add the exponents, so it makes sense that you can split this up into a to the x times a to the h. So probably the next logical algebraic step here is to factor out the a to the x in the numerator, in the numerator. Now if we look at this expression, we're trying to take the limit as h goes to 0. And a to the x is constant with respect to h, right? It doesn't matter what h is, a to the x remains a constant. So we can factor that out and put it in front of the limit expression, and we get a to the x times the limit as h goes to 0 of a to the h minus 1 over h. Now, if we try the old tried and true plug it in and see what you get kind of thing, if we put in h equals 0, we get 1 minus 1, which is 0, 0 over 0. And in order to properly calculate this derivative, we need to use something called L'Hopital's rule, which you'll get either late this quarter or early next quarter, or semester, excuse me, in Math 28. But let's just hang with this expression right now and see if there's some use that we can make of it. Okay. So I'll just copy this from the previous page. This is just what I had, that a to the x, the limit as h goes to 0 of a to the h minus 1 over h. Now, let me change gears a little bit here. If we take the derivative at x equals 0, so before I was taking the derivative of the function, now I'm taking the derivative of this function at a particular value, where x equals 0. So then I'll do the same thing, plugging it in, and then I get this a to the 0 plus h minus a to the 0 over h. And I'll do the same thing that I did before. I'm going to factor out that a to the 0 power, and then rewrite that a to the 0 equals 1. And so we have this derivative here, the derivative of an exponential function at 0 is this expression, which is the same expression that we had up here. So let's make a substitution. Let's get rid of this limit expression and then put in f prime at 0. And what we're going to get then is the derivative of the function is going to be the derivative at 0 times the function. So there's really only one point that we need to know, and so we have the derivative of an exponential function is proportional to the function. Okay? See the significance of this? I'm not taking the derivative directly of a to the h. What I'm finding, a to the x, what I'm finding that if I know the derivative at f prime, if I know the derivative at 0, then I'll know what the derivative is for the entire function, because that function's derivative is proportional to the original function. So this is significant.
When you move the a to the x in front of the limit, that is like only acceptable because it is at 0? That's why we're able to do that?
Well, right now I've eliminated it because a to the 0 is 1, and so I've just dropped the 1. What I did on the previous page was the same thing as if I had this. If I had the limit as h goes to 0 of some number, 3 times some expression in h, that's going to be 3 times the limit as h goes to 0 of that same expression. So when this is a constant, remember, we can factor that out, just like we do when we do derivatives or integrals. You know, constants just kind of ride along. Now, when we had a to the x, you say, well, that's a function. Well, with respect to what you're taking the limit of, h, it is constant. So at any particular a to the h, or a to the x, it makes no difference what h is, and so you can bring that out.
Wait, so does it become one, this is the right word, does it become one expression? Because I always thought of the limit as sort of separate. Like it's not, you're not gonna multiply by it, at least not with the rest of the expression. Are we now multiplying the constant by the limit somehow, by the?
Yes, you can factor out a constant is the operative thing there. It's that you can take, let me see if I can get you a little bit more tangible example. So if the limit as h goes to 0 of, let's say, x times 1 plus h, okay? So if we were to evaluate this the normal way, this would be equal to just x, right? Because h would go down to 0, we'd have x times 1. The other way that we could do this is that since x is independent of h, you can factor this out. And so what you get now is, as h goes to 0, this becomes 1, so we have the x times 1. It's exactly the same thing that we're doing here, where we're taking a to the x is independent of h. And so that's why I could factor it out. Okay, so my statement in purple, the rate of change of any exponential function is proportional to the function itself. All right. So let's look at some graphs of functions, and we can generate these graphs numerically. And so I have three functions here. I have f at x equals 2 to the x, g at x equals 3 to the x, and h at x equals e to the x. Okay, so as expected, as the base grows larger from 2 to 3, it becomes more steep. So in other words, the functions get larger quicker, and they also go down to 0 more quickly when x is negative. Okay, so if we look at this point, and we can calculate what f at x is, or what the derivative is, numerically. Okay, so we can do this by taking, let's say, we can evaluate the difference ratio, which is the thing that's inside the limit when we're calculating a derivative. We can calculate these numbers closer and closer to 0, and essentially what we're doing is making a linear approximation. And it turns out that the derivative at 0 is going to be 0.6931. And then if I do the same thing with g at x, it's going to be, the derivative at 0 is going to be 1.0986. The significant part here is that that derivative, f prime at 0, or the function at 0's derivative, we can define e to be a value of 1 at that point, okay? And in fact, that's what it turns out to be, that h prime at 0 equals 1. Now this is, I do this by assuming what e is, and in fact I can actually declare what I want e to be by saying I want the derivative of that function to be 1 at 0. They haven't mowed the lawn in 2 weeks. Thanks.
So but with e itself, h prime is always 0, or 1, right?
Okay, so I'm going to turn this around the other way. And I want to define e this way. I want to say the limit as h goes to 0 of that difference equation is 1. So I'm ignoring what I used to know about e, and I'm saying I want e to be that. And that's a perfectly good definition, and you end up with e being that 2.7 value that I discussed earlier. So, you know, it has the same value as when I had this expression earlier that I showed you, or the sum of that infinite series that I showed you. And in fact, there's a whole bunch of ways that you can arrive at e. Some of them are easier to compute than the others, but they are all the same e, and this is a very special number in that regard. You know, pi is special for one reason. It's the ratio between the circumference of a circle and its diameter. E is a special number because it comes out of all sorts of different places in calculus. And so one of the things that that I'm declaring here is that I can define e to be when I have my exponential function, I want this slope to be 1. And so that's how I define e, is that's the function that gives that to me. The function in the form f at x equals e to the x. I'm declaring that e is the value that makes this true. Okay, so this may seem a little esoteric from a mathematical standpoint, and perhaps it is. Yes?
The last slide, can you assume that the derivative is wherever it hits the y-axis, or is that just...
I want to compute the derivative at the y-axis. So,
okay,
you know,
it's
the
not
derivative's going to be,
derivative.
yeah, the derivative's going to be different at every point there. But I'm saying I'm interested in the derivative at that point because what I did before on that was I found that if I knew the derivative at 0, that I would have the derivative explicitly because I know that you take the original function, multiply it by its derivative at 0, and you get the derivative of the function then. Okay, so that was the whole point of going through this exercise, that we can, you know, look at what happens when f prime, or when x equals 0, what does f prime equal? And then we have this relationship that says, now we can figure out what the derivative is just by knowing f prime at 0, because it's proportional to the original function. Okay, so we have those definitions. Okay, so that's what we have out of all this mess. So we're saying that I want to make a special value e, then we'll know that the derivative of that function is going to be 1 because we know the derivative of this at 0 is going to be 1. And so we just simplify that to be e to the x. And so we have what that is. So now, what's the rest? How are we going to find the derivative of all these other functions when it's not e? And so October 10th is scheduled on our schedule that we'll talk about what the derivative is when a is not e. I can tell you the short story of that is that we just use the chain rule, and then we find the chain rule is going to require us to know the inverse of e to the x, and so we'll get to that point. The day before, October 8th, the lecture before, we'll be reviewing things like the chain rule and the product rule and all those kinds of things. Okay, so for now, this is the theoretical basis of the derivative of e to the x, and we'll stop there.